So in this third and final flipped lesson on waves, we're going to look at light and electromagnetic waves. Light is one example of an electromagnetic waves, but there's also lots of other important examples of electromagnetic waves. And we're going to look at some of the phenomenon and behaviour that we see with those. Let's get into it. So let's start by looking at what is light, or what is an electromagnetic wave. We'll focus on that on this slide. And then on the next slide, we're going to focus on some of the phenomenon that relate to light and electromagnetic waves. And one of them that we'll look at also applies for mechanical waves, just in the same way as I say interference can apply for both mechanical waves or electromagnetic waves. But I've sort of left it for electromagnetic waves. You'll notice here I've crossed out some things. I've just copied this directly from the SACE subject outline. You don't need to do everything in the SACE subject outline. I have focused on the phenomenon that are related to things that we will need to know heading into Year 12 physics, and the ones that I see as most important. The stuff that I've basically left out and skipped over is stuff related to refraction and the ray model of light. That is about basically how lenses work and glasses work, and also how they make optical fibres. It's all really interesting stuff. It's also important physics. I'm not trying to devalue it. If we have time and people are keen, I will give you some work that you can look at that at the end, but it won't be part of your formal assessment for this term. But, you know, it is very much related to this topic, is, all that stuff on refraction and lenses and internal reflection and binoculars and all sorts of things like that. Optics, all that sort of stuff is related to refraction and the ray model of light. But we're going to focus really here on things that relate to light behaving like a wave, and in particular electromagnetic wave, just because it fits in better with our focus and what we need to know for next year. But if anyone is keen to learn more about that other stuff, once we get through this, please let me know. There's plenty of work that I can give you. There's stuff in the book that you can do to look at that. Okay, so what is an electromagnetic wave? Electromagnetic waves consist of oscillating electric and magnetic fields. Radio waves, light, UV, X-rays, gamma rays are all examples of electromagnetic waves. We could have thrown in things like infrared as well. If we look at this down here, this is what we call our electromagnetic spectrum. We start out here with the very long wavelength. We have things like AM radio, FM radio, your TV signals all come on this area. Radar is used here. This diagram is probably a bit old, but this is also the area where you'd find the sort of waves that are used in mobile phones, in Bluetooth, in Wi-Fi. All of those sort of sit in this radio waves end of the spectrum. Then we get down into the infrared. You've probably got infrared is what controls your remotes at home. We can't see infrared with our eyes. A good little experiment that you can do though is if you get a infrared, a remote control, and press the button in front of your phone, you'll often be able to see the infrared because the cameras in the phones can pick up some of that infrared that our eyes can't pick up. Then we get into this very narrow part of the spectrum called visible light. This just happens to be the part of the spectrum our eyes can detect and what we see as the colours of the rainbow. Red, orange, yellow, green, blue, indigo, violet. If we go past that and we get into the shorter wavelength, we get into ultraviolet. And then if we keep going into even shorter wavelengths, we get into X-rays, which we know obviously can go through our body, and then into gamma rays, which are associated with radioactive decay and either can cause cancers or treat cancers as well. So what we see here as we go across, we are getting lower wavelength. That means we are getting higher frequency. So as the wavelength decreases, the frequency increases, and as the frequency increases, the energy increases. So these things here that can penetrate our skin and cause sunburn and cause cancer have a lot more energy than things like AM and FM radio and TV signals and mobile phone signals, etc. Which is probably a good thing because we're exposed to a lot of these things and we wouldn't want them to do the same damage that UV does to us. So, an electromagnetic wave, all electromagnetic waves travel at the same speed in a vacuum, and air is almost the same as a vacuum, and that is 3 times 10 to the 8 metres per second. So that's 300 million metres per second, or 300,000 kilometres per second. The wave equation can be used to determine the relationship between their speed, frequency, and wavelength. That's V equals F lambda. And in that case, we often use the word letter C for the speed of light. So sometimes you'll see C equals F lambda. C is just the symbol for the speed of light. You might have seen that in the famous E equals MC squared formula. So if you want to have a bit of a picture of what an electromagnetic wave looks like, we have this electric field here in red that's oscillating. That creates a magnetic field at right angles to it that also oscillates, and this wave just propagates through space. I'm not going to talk too much about what electric fields and magnetic fields are this year. That is a whole topic next year, so you'll learn a little bit more of an understanding of what an electric field and a magnetic field is. But at the moment, we just need to understand that these fields are what makes up electromagnetic waves. They oscillate at 90 degrees to the direction of travel, so they are transverse waves and they behave like transverse waves. I think I've said all that. Increasing wavelength, decreasing wavelength, increasing energy. We've got our electromagnetic spectrum. So let's really now look at some of the phenomena that relate to electromagnetic waves. Now, I haven't got this information on the next slide, so I will just pointing that now, but we're going to look at some of the things that are mentioned here in the next slide. Let's get into it. So the first one I'm going to talk about is polarization. Polarization refers to the direction of oscillation, and by definition we say the electric field of an electromagnetic wave or light. Let's just think about light as the easiest example. So generally light is not polarized. When we're seeing light, it is vibrating in all different directions. But the thing about polarized light is it all vibrates in the same direction. Easy way to demonstrate that is using some Polaroid filters. So these are the sort of filters that would be used in polarized sunglasses. So this Polaroid filter, for example, would only let light going through that's oscillating in one direction. So at the moment, let's say it's letting all the vertical light go through. Is that better to demonstrate like that? The vertical light going through. So at the moment, it makes my face look a bit darker when I'm behind it because it's not letting all the light that's reflecting off my face through to the camera, but you can still see that light being reflected off. If I get another one of these filters and put it here, again, you can still see my face because there's two of them. It's stopping a bit more of the light getting through, but whatever light first one was letting through, the second one is letting through light in the same direction. But if I spin one of those 90 degrees, it's like a game of now you see me, now you don't. Now you see me, now you don't. Now you see me, now you don't. So what's happening here now is this filter, say at the back, is letting through the horizontal light. This one at the front, the one at the back is letting through the vertical light. The one at the front is only letting through horizontal light. Basically, all of the light gets filtered out because all that gets through this one is the vertical, so there is no horizontal left. So all the horizontal gets filtered out by the second filter. So if you're ever buying sunglasses and they say they're polarized and you want to check, if you just grab two pair of polarized sunglasses and do this trick, rotate them 90 degrees, if it goes black, That'll tell you whether they are definitely polarized or not. So that's what polarization looks like. I've got it described in words on the next slide, and then I'll talk about some of the other ones. Let's keep moving. Okay, so just continuing on here. Polarization, it's really just summarizing what I said before. In an electromagnetic wave, the plane of polarization refers to the plane in which the electric field oscillates. Polaroid filters, e.g. Polaroid sunglasses, only allow light travelling in one plane to pass through. This is the bit I didn't talk about. As reflected light is partially polarized, you don't need to know how and why that happens. They can be very useful to reduce light intensity and glare. So again, when we catch up, we might look at this. But if you get glare, which is obviously reflected light, say off a shiny windscreen on a car or off a window or the water even, the Polaroid filter will filter out some of those orientations so that you can't see those anymore. And basically it can take out that glare, that reflected light, without actually taking out what you might call the natural light that comes with it. So that's another reason that Polaroid filters are useful. The next thing we want to have a look at is diffraction. This doesn't look all that amazing in real life, so I won't bother doing a demo for it. But it's the deviation from straight line propagation that occurs when a wave passes through a narrow aperture or past a sharp edge. So particularly we would do it with laser light that travels in a constant direction. If you put that through a narrow aperture, you'll see those waves spread out. If it's a smaller aperture, you'll even see it spread out more. Similar thing happens if it goes past a sharp edge. Instead of just going straight on, that light will start to spread out as it goes past a straight edge. Again, we don't use diffraction a whole lot this year, but it does become very important next year. Basically, we look at the combination of diffraction and the interference of light together. So that's why it's important to know just briefly what diffraction is at this point. And the final one I'll talk about is the Doppler effect. Now, this one applies with both mechanical waves like sound waves, and it also applies for light. If you've ever had that phenomenon of either hearing a siren coming towards you or even a car coming towards you, and it sounds different when it's coming towards you, you hear a higher pitch sound when it's coming towards you, and then you hear a lower pitch sound as it goes away from you. So you get that sort of, and then it goes past you to, I probably exaggerated that a bit. Why does that happen? That's the Doppler effect. If you can imagine, this is something that's releasing sound and it's travelling this way. So say you're standing here and it's moving towards you. And say if it's sound waves, those waves are coming out at you at 340 metres per second. But say it's travelling really fast. So say it's travelling at 100 metres per second. That would mean that as it's travelling towards you, basically those waves get compressed together because it's actually between when it releases the waves, it's got closer to you. So in a sense, the waves on this side will be closer together. If the waves are closer together, there will be more waves per second, so we'll see a higher frequency. Then when it goes past you, those waves are getting spread out because in that time between the waves have travelled, it's gone a little bit further that way, so those waves effectively get spread out more, and we then hear a lower frequency sound. So that Doppler effect, as I said, it explains often those difference in sounds that you'll hear between an object moving towards you and moving in away, particularly if it's moving at high speeds, like a car on the highway or a plane or particularly a police or an ambulance, something like that might be moving at high speed and emitting a sound. It's also very important for light. This is sort of how they worked out the universe was expanding. So maybe I'll just read out what I've got here rather than talk about it and then read it out again. So the Doppler effect is a measurable shift in frequency or wavelength of a travelling wave caused by the relative motion of the source and the observer. As a source of waves, whether it's sound or light, approaches an observer, the waves are compressed and the apparent frequency is higher. The opposite occurs if the source recedes from the observer, so moves away from the observer. Light behaves in the same way. Stars with relative to motion towards an astronomer appear blue. So if we're looking through a telescope at stars and it's heading towards us, it'll appear bluer than it is because bluer is the longer wavelength. The entire spectrum of the star shifts, light shifts towards the blue end of the spectrum, or is what we call blue shifted. Stars speeding away from the astronomer appear red shifted, i.e. the entire spectrum is red shifted. This is how astronomers know the universe is expanding. Almost everything is red shifted, so we know most things are moving away from us, not towards us, because they're red shifted. This, again, I'll give you a simulation to look at that sort of maybe better demonstrates this than I can just by explaining it, not that it's that complex. This phenomenon also leads to what causes sonic booms when we talk about sound waves. So why we get that sonic boom when, particularly an aircraft normally it is, or a bullet, for if you're looking at smaller projectiles, breaks the speed of sound. I won't try and explain it with this diagram, but it is just an extension of the Doppler effect. So please make sure you ask me about that if you're interested. Okay. That's the core of what you need to know for the waves topic. As I said, looking at some of the other simulations that I'll give you to look at, and obviously doing the questions and doing some practical activities, which will also hopefully add to your understanding of this. And as I said, if you are if you're interested in learning more about refraction and the ray model of light, I'll give you an opportunity to explore that at the end, but we won't do that as part of our assessment. We'll get this all out of the way and our assessment finished before we do that. Cheers.